Alright, here we are, Falcons, for the second Christmas video to review our skills in calculus. Today we're going to be talking about limits. So, there's basically three types of problems with limits that we're going to be working with. The first is just direct substitution. We just plug in whatever value it tells us to, basically. Whatever x is approaching, we plug in, we see what value we get, and then there's basically three results that can happen. Alright, so we're going to see what could happen and what that means and how we come up with our answers. So let's just start off with a basic limit question. What if we had the limit as x approaches 3 of x plus 2 over x minus 5? So first thing we always try is we just try to plug in whatever value x is approaching, in this case 3. So if we substitute in 3 in the numerator, we obviously get 5. If I do the same thing on the bottom, 3 minus 5 is negative 2. And notice 5 over negative 2 we can simplify to negative 5 halves. There's no more we can do to simplify that. So that is our answer. Now, we're not always going to get negative 5 halves. We can get something else. Alright, so that's when we need to understand what we can do based on the answer we've come up with. If we get an answer that's negative 5 over 2, where that is something that can actually exist, that is our answer. However, if we were to come up with an answer such as 5 over 0, well, are we allowed to divide by 0? Of course not. So that means this answer, if we did get it, would be the limit does not exist. However, if we got 0 as the numerator rather than the denominator, and let's just keep the denominator 5 this time, well, 0 over 5, that's actually 0. So the limit here would just be 0. And then the final case that does pop up quite a bit for our calculus problems is if we come up with 0 over 0. Now, 0 over 0 is not 0, and it does not exist. It could be either of those, but in this form, 0 over 0, when we've directly substituted and we get 0 over 0, that just means it's indeterminate. Okay? That means we cannot figure out, based on this, if it's an actual number, if it does not exist, so we need to do something else. What we're going to be doing to figure it out is either usually factoring, or we can rationalize the denominator to see if we can come up with something else. So let's try a factoring example just to see what happens. So, a factoring example. If we had the limit as x approaches 1 of x squared plus 2x minus 3 divided by x minus 1, looks like a pretty easy factoring example. So usually what's going to happen is the denominator is going to be one of the factors of the numerator. So if we tried that out, we might as well try that out first, is if I do x minus 1 on the top, well, what number would add up to 2? Or if I added it to negative 1 and give me 2 and also multiply to negative 3, the answer here is obviously positive 3. So x minus 1 and x plus 3. And we have x minus 1 on the bottom. So obviously the x minus 1s can cancel, and so the only thing left is x plus 3. So really, it's just the limit as x approaches 1 of x plus 3. In this case, we plug in 1, we come up with our answer of 4. Now, I did neglect to do one quick thing, because I knew what was going to happen, because I created the problem. The first thing we should always do is substitute the 1 into the question to begin with. I skipped that part because, like I said, I knew what the answer was going to be. I knew it was going to be 0 over 0, and if you in fact take the time to plug in 1 into the numerator and denominator, you will realize that you get 0 over 0, which, like I said, is indeterminate, which required us using some factorization. Once we factored it, we then plugged the number in again, and this time it gave us 4. The reason why this works conceptually is because if I was to take x plus 3, or rather, let's take the original. Okay, if I was to graph this, well, here's what's going to happen. It's going to be x plus 3, so a y-intercept of 3, and it's going to have a slope of 1. So if I go over 1, it's going to go up 1. However, at x equals 1, the graph will not exist because there's going to be a hole in the graph. So our original function is going to look like that. Now, if we're taking the limit as x approaches 1, this is a general limit, so it has to approach the same thing from the left side and the right side, in which case it does. From the left side it approaches 4, from the right side it approaches 4 as we're approaching 1. Um, the point doesn't actually have to exist for there to be a limit there. Okay, if we're talking about the derivative, that's another story entirely, but in this case we are talking about limits, and the point doesn't actually have to exist for there to be a limit there. Remember when we learned this originally, we talked about the diner example where the two people were going to the diner was gone, it had vanished, their favorite restaurant just poof, gone. The fact that they were still both going to the diner meant though that it was still the limit. So in this case, the limit would be 4. All right. The next example we're going to do some rationalizing. So if I look at my example here, the example we're going to be trying is the limit as x approaches -2 of radical x plus 3 minus 1 over x plus 2. Now, again, I don't want to do the same mistake I made last time. So if we verify, if we plug in -2 into this function, if we get an answer, that's our answer right there. We can stop. We don't need to do any more rationalization or anything. We're just done, which would be ideal. But obviously, that's not going to be the case most of the time. If I plug in -2, well, -2 plus 3 would be 1. Radical 1 is 1. 1 minus 1 is 0. And if I plug in -2 into the denominator, -2 plus 2, obviously 0 again. So it is indeterminate. So notice, I plugged in -2. I did get an indeterminate answer, which then necessitates another step if I want to find the limit. In this case, whenever you see radicals, you're going to be rationalizing for the most part. So rationalization means you're going to take the conjugate of whatever you want to rationalize, which in this case is the radical x plus 3 minus 1. So the conjugate of radical x plus 3 minus 1, conjugate just means keep the first term the same and the opposite of the second term. So I'll keep the radical the same. The -1, though, is going to turn positive. So what it's going to look like is the limit as x approaches -2. We're going to keep this guy exactly the same, multiplying it by its conjugate, like we said. The radical stays the same. That was the first term. The second term turns into its opposite. And on the bottom, we're going to have x plus 2. But if I multiply by the conjugate on the top, I better multiply by the exact same thing on the bottom so that we're really only multiplying by 1. So I'm going to keep, or rather put, the radical x plus 3 plus 1 on the bottom. All right, notice here how if I multiply and divide by the same thing, I'm really not doing anything. I'm just manipulating rather than changing. So we're actually going to FOIL out the top. The neat thing about conjugates, though, is that whenever you multiply conjugates, the middle terms are going to cancel. So I know that, so I really only have to multiply the first terms and the last terms. If I do that, we get the limit as x approaches -2. Radical times radical. When I do that, it's just whatever's inside. So we get x plus 3. And then doing the last terms, -1 times 1 is -1 over. Now, we could multiply x plus 2 times radical x plus 3 plus 1. We could. The thing is, though, when you do rationalization of limits, you don't need to do that. We're just going to skip that step, and we'll see why in a second. If I just leave it as x plus 2 multiplied by radical x plus 3 plus 1, well, what does the numerator simplify to? X plus 3 minus 1. If I add like terms, the 3 minus 1 is 2. So really, do you see how the top is really just x plus 2? Which means this guy cancels with that x plus 2. So now I have nothing left on the top except I was dividing by it. So it's not going to be a 0, it's going to be a 1. So we get the limit as x approaches -2, let's move it up a bit, of 1 over radical x plus 3 plus 1. Notice the 1 is not inside a radical. And now that I've rationalized and I've canceled, we're going to see if I can plug in -2 now and what type of answer I get. Hopefully this time it's an actual number rather than indeterminate. So if I plug in -2, we're going to get 1 over radical -2 plus 3 plus 1. Let's just simplify. -2 plus 3 is 1. Radical 1 is 1. So it's really 1 over 1 plus 1, which obviously is 1/2. So that is the limit of the original function all the way up at the top. So the limit as x approaches -2 of radical x plus 3 minus 1 over x plus 2 is 1/2. So we've covered the 3 types of problems we need to go over for limits. Here's what you're going to be doing now in your In a separate sheet of paper, you're going to be doing the second homework assignment for Christmas break. I know, homework over Christmas, what a drag, but you guys are the Valley All-Stars. You guys are going to do an excellent job, I'm sure. Here's the question I want you to attempt. Okay, it's not that bad. If you paid attention to me rationalizing, you should definitely be able to do that one. So notice it's two limits you're going to take, and you can do them separately, and then you just add them together and see what answer you come up with. The first person that can find for me the simplified answer to this question will get a shout out, and also they can get some extra credit homework. I'll give them a free homework assignment for calculus once we come back from the break. All right, sound good? Okay, hope you're having an excellent Christmas break so far, and keep up the good work, guys.